In the last video, we talked about the concept of resonance, or the sharing or delocalizing of electrons. This provides us with different contributing resonance structures, and what we learned is that even though we can draw often several different resonance contributors, each of those by themselves really has no representation in reality. The true structure is what we call the hybrid structure, which is a weighted average of all of the different resonance contributors. Okay, we learned how to draw resonance contributors, how to use curved arrows to move electrons, to convert one resonance structure to another, and we learned how to evaluate the relative stabilities of different resonance contributors. In this video, what we're going to do is we're going to look at a special class of molecules that have a lot of resonance. So they're special because of the resonance. And these are compounds called aromatic compounds. And like I mentioned last time, kind of the prototype of aromatic compounds is this one here. And this is called benzene. Alright, so in this chapter we're going to talk about benzene. We're going to talk about what it takes for a molecule to be aromatic, and then we're going to look at some different aromatic compounds. So benzene itself was a big challenge to organic chemists back in the mid to late 1800s. This slide shows us some of the basic data that they were working with. For one thing, the formula they determined is C6H6. And so what can we say about this type of formula? Right, so this type of formula has lots of unsaturation, right? Because remember that for hexane also has C6. Let's do cyclohexane here. Well, we'll just do hexane. How many hydrogens does hexane have? Okay, remember for alkanes, the formula is Cn, so n is 6, 2n plus 2. So 2 times 6 is 12, plus 2 is 14. All right, so remember for the loss of every 2 hydrogens, we have an unsaturation. So if we subtract 6 from 14, we get 8, and that's divided by 2. This has 4 unsaturations. All right, so how do we come up with a structure that has so many unsaturations in such a relatively small molecule? All right, so here's some other information that they were able to determine. In this structure, all of the carbon-carbon bonds are equivalent to one another. All right, so that means there has to be a lot of symmetry in the molecule. And the carbon-carbon bond lengths are in between single bonds and double bonds, right? So they aren't discrete single bonds or double bonds. Remember, we know that carbon-carbon double bonds are shorter and stronger than carbon-carbon single bonds. As well, all of the carbon-hydrogen bonds are equivalent. All right? So there needs to be a lot of symmetry in this molecule. As far as reactivity goes, they found that that if we just react benzene with bromine, right, so try to do an electrophilic addition reaction just like we did for other alkenes, they got no reaction. Okay, so benzene isn't reactive with just bromine. However, if they were used a catalyst, they could get a reaction to take place. However, instead of getting an addition reaction, which we would expect, one hydrogen on benzene was substituted for a bromine. All right, so they got a substitution reaction, rather than an addition reaction. So that was unusual. If this product was reacted again with bromine in the presence of the catalyst, they could add 2 bromines here, but they would get 3 distinct products. Alright, so not just 1, 3 different products. Alright, so chemists came up with lots of different types of structures, really crazy structures, that could account for this type of formula at least. So there's about a chemist, a German chemist, August Kekule, who had a daydream, I guess, or some type of dream. And in his dream, he imagined a snake eating its own tail, like this. And that led him to come up with a cyclic structure for benzene that's shown here. Alright, so I have it drawn over here, and so we know that each of these carbons would have 1 hydrogen attached. Just by definition, how we do our skeletal structures, right? The thing that isn't immediately explained using this model is why all of the carbon-carbon bonds are the same, right? Because what we would really expect in this case is that for the carbon-carbon double bonds to be shorter than the carbon-carbon single bonds. All right, so the next level of this, the explanation, is that we have resonance. All right, so what we can look at is just like when we had conjugated pi bonds, or pi bonds that are next to each other. In these cases, we can move these double bonds. If we move this one over, of course, this next carbon can't hold any more electrons, so it has to move its electrons over. Same thing happens again, and we come up with a different resonance contributor that looks the same, but it just has all of the double bonds switched by 1 position. All right, so if we do a hybrid of these two, then each of those carbon bonds are going to be the same. They're going to be, since they're a double bond in one and a single bond in the other, they're all going to be partial double bonds like this, and they should all be the same length. Alright, so if we look at this type of structure, what we're going to expect is that each of these carbons is sp2 hybridized, right? So it's trigonal planar. 2 of the sp2 bonds are used to make carbon-carbon bonds, right here, and the third sp2 hybridized bond goes to the hydrogen. All right. What that leaves over, remember, is an p orbital. So each of the carbons around the ring has a p orbital, okay, like this drawing right here. Each of those p orbitals is contributing a single electron. All right? And so if we look at this structure, we wouldn't know, right? If we see 2 p orbitals, we could say, oh, there's a pi bond there, and a pi bond here, and a pi bond here, right? But we couldn't tell, really, because there could be a pi bond here, here, and here. So what we really have is a delocalization of the pi electrons around the ring. So it kind of looks like there's just these 2 donuts on the top and the bottom of the ring. All right? So this type of delocalization has some practical consequences. If we use a measure that we did before when we were looking at stability of alkenes, right? We looked at heats of hydrogenation. Oops. we can get an idea of how much energy is saved, or how much resonance energy is saved in this process. Okay, so try to follow this analysis. Okay, so we can start over here by recognizing, let's do this in red, by recognizing that when we do a hydrogenation reaction of an alkene, so if we start with cyclohexene, we add 2 hydrogens, we go down in energy, right? It's an exothermic reaction, and in this case it gives off 28.6 kilocalories per mole. All right? So, without resonance, what we might imagine that if we had 3 double bonds in this ring, then the amount of heat given off in heats of hydrogenation would just be 3 times that, right? So 3 times minus 28.6 would give minus 85.8. All right, so this would be maybe what would be expected. Right? Just 3 double bonds, unrelated with one another. However, if we measure the heats of hydrogenation for benzene, we see that it only gives off 49.8 kilocalories per mole. So this is a much less exothermic reaction than what was expected. So that means, since we're getting the same product in all of these cases, cyclohexane, that benzene right here is much lower in energy than this kind of theoretical cyclohexatriene. Okay, so the difference in energy between the theoretical one here, which would have localized electrons, and benzene, which has delocalized electrons, is 36 kilocalories per mole. Okay, so this is what we would call the resonance energy. Okay, so that's a lot of energy savings because of resonance. And so this difference is what really controls all of the reactivity, the difference in reactivity versus just isolated alkenes that aromatic compounds have. Alright, so benzene is not the only aromatic compound. Alright, so here's benzene over here. We can have substituted benzene, so essentially a benzene with different groups attached. Some of these are interesting. You've probably heard of them before, or know of them. So this first compound, look, this is an aldehyde. Has an alcohol on a benzene ring. It's called a phenol. And it has a methoxy group. Okay, this compound is called vanillin. So where do you think that comes from? Okay, this comes from vanilla. Okay, from vanilla beans. This is the smell, the aroma, and the taste of vanilla. Okay? So the next compound over here, notice it just has this one kind of unsaturated side chain. It has an alkene and it has a carboxylic acid here. Okay, this is called cinnamic acid. So where does that come from? This one comes from cinnamon. This is the smell and the taste of cinnamon. Okay, and so notice that both of these compounds have very good and interesting aromas, and so I think this is where the original term of aromatic came from. Alright, so aromatic compounds can also have more than one benzene type of ring. Alright, this one down in the lower left is called naphthalene. Alright, and this is the component in mothballs. I don't know if anybody's ever smelled that before, but it has a unique kind of characteristic odor. And this other Last one, look, it has 3 benzene type rings, and this is called phenanthrene. Okay, when we start to get more and more rings, we can call these polycyclic aromatic compounds. Alright, sometimes these polycyclic aromatic compounds are carcinogenic because they have planar structures, just like benzene, and they can interact with DNA. So DNA has these base pairs that are stacked into this alpha helix, and this planar molecule slides right in between the DNA base pairs. It's called intercalation, and it can cause DNA damage. Alright, so we've got various aromatic compounds here. What does it take to join this aromatic club? Alright, so there's a number of different criteria. Okay, first off, the molecule must have what's called an uninterrupted cloud of pi electrons. Okay, this is kind of the donut on the top and the bottom that we showed for benzene. In order to have an uninterrupted cloud of pi electrons, it needs to be cyclic, at least it needs to have a cyclic structure as part of the structure. Right? You can have various other things attached to that. Every ring in this cyclic structure has to have a p orbital on it, okay? And the cyclic structure needs to be planar. This allows all of those p orbitals to be lined up so we can have delocalization of electrons. In addition to this, the cyclic structure needs to have a certain number of pi electrons. Okay, so this pi cloud that we talked about up above must have an odd number of pi electron pairs. Alright, so let's look at, well, let's just start out with benzene itself. Okay, so we can count pi electron pairs just by looking at the double bonds in this ring. So this has 3 pairs of pi electrons. Okay, so an odd number. We look at naphthalene. It has 1, 2, 3, 4, 5. Right, so we have 5 pairs of pi electrons. Okay, what about phenanthrene? 1, 2, 3, 4, 5, 6, 7. Okay, so it has 7 pairs of pi electrons. Okay, another way to come up with essentially the same calculation is called the Huckel's rule. All right, and that says that the total number of pi electrons in this ring has to fit into this equation 4n plus 2, where n is just some integer. Okay, so for example, if n equals 1, then we have 1 times 4 plus 2, we have 6 pi electrons. So let's look at benzene. All right, so now for each of these pi bonds, there's 2 electrons, 2, 4, 6. All right, so let's make a little table over here. If n, here's n, and here's pi electrons. If n equals 1, then the number of pi electrons is 6. This has 6 pi electrons. Okay, if n equals 2, 2 times 4 is 8 plus 2 equals 10. If we had 5 pairs of electrons in naphthalene, this would have 10 pi electrons, right? 2 times 5. If n equals 3, 3 times 4 equals 12 plus 2 equals 14, right? Phenanthrene has 2 times 7 pairs. It has 14 pi electrons. Okay? So all of these fit. The numbers for N aren't any numbers that we count from looking at the structure. This, just by going 1, 2, 3, 4, 5 on up, this just gives us the possible numbers of pi electrons that could make a molecule aromatic. Okay? So if we carry on here, if we look at this, so N can also be 0. So this would tell us that, in theory, we could have a molecule that has 0 times 4 is 0 plus 2 has 2 pi electrons, and it can be aromatic. Okay? If molecules follow all of these criteria up here, but if they have an even number of pairs of electrons, or the number of pi electrons equal 4n, then the molecules are called anti-aromatic. Okay? And anti-aromatic molecules are very unstable. Okay? So oftentimes they don't actually form because they're too unstable. But here's 3 examples that would fit in with this. Okay, so the first one here, this is cyclobutadiene, right? So it has 4 carbons in the ring. How many pairs? It has 2 pairs of pi electrons. Or how many pi electrons does it have? 2 times 2 is 4 pi electrons. Okay, so this falls into 4n. So if n equals 1, 1 times 4, that's a number of pi electrons. So this would be anti-aromatic. And in fact, it's very unstable. And chemists tried for years to synthesize this molecule, but it's very difficult, and they never have been able to synthesize it by itself. They've had to add various groups around it to help stabilize that structure. All right, so the next one would be the cyclopentadienyl cation. All right, so look, it has 5 carbons in the ring, but how many pairs of electrons does it have? Okay, it only has 2 pairs. Oops. 2 pairs of pi electrons. Gives it 4 pi electrons, even though it has 5 atoms in it. Right? So this one is just has an empty p orbital. So this is also anti-aromatic as long as it's planar. So then the next one, cyclooctatetraene. How many pairs? So this has 4 pairs of pi electrons. It has 8 pi electrons, right? So that fits into 4n if n equals 2. All right, so this would be anti-aromatic, but in fact, this molecule can form, but if it does, it breaks the rules to become anti-aromatic. In fact, it bends out of the plane and makes something like this. Okay? In this way, it can exist, but not be anti-aromatic. All right, so let's look at some molecules. We can have different types of aromatic or anti-aromatic compounds. So in each of these structures, what we're going to look for is we want to decide, for one, whether they're aromatic, whether they are anti-aromatic, or whether they're just simply not aromatic or anti-aromatic. All right, so let's start in the upper left. Is this molecule aromatic, non-aromatic, or neither? All right, so the criteria, remember, it's ring, yes. Has to have a p orbital on every carbon. Does that satisfy this? No, because remember, in this structure, there would be 2 hydrogens here because this is an sp3 hybridized carbon. All right, so this is not either aromatic or anti-aromatic. All right, this next compound is one called pyridine. All right, and so when we analyze these, we have to figure out what electrons are available, right? So the nitrogen here, when we have nitrogen with 3 bonds to it, it has a non-bonding pair of electrons on it. Okay? So what we have to decide then is whether those non-bonding electrons are part of the pi system. All right? Because if we want to count pairs of pi electrons, if we count 1 pair, 2, 3, that could be aromatic, but if we count this pair as well, that would be 4, that would make it anti-aromatic. Okay? So are those non-bonding pairs, are those part of the pi system? Okay, and the answer is no, right? So this molecule is kind of like benzene. Let's draw this on its side. Okay, and what we essentially have is that each carbon here has a p orbital, right? They all have double bonds going to it. The nitrogen already has a double bond going to it as well, so it has a p orbital here. All right? Each of the carbons is donating, and the nitrogen, each one of these is donating 1 electron. Right? Because we need 2 electrons for each pi bond. And those non-bonding pairs, where would that go? Okay, so that would go in the sp2, in the sp2 hybridized orbital, right? So for example, for benzene or for any of these other atoms around here, that orbital would go for a carbon-hydrogen bond. But for nitrogen, because nitrogen has an extra valence electron, we end up just with a non-bonding pair. Okay, so this answer is yes. So pyridine is aromatic. All right, what about this next one? Look at how many carbons do we have. We've got 1, 2, 3, 4, 5, 6, 7 in a ring. Cyclohepta, and it's got 3 double bonds, heptatriene enol cation. Okay, so how many pairs of electrons do we have in here? Pi electrons. We have just those 3 double bonds, so we have 3 pairs. Pi electrons gives us 6 pi electrons spread over 7 atoms, and so yes, this one is aromatic, right? Remember that when we have a carbocation, it's sp2, which means that it has a p orbital on it. Okay, so let's look at these bottom 3. All right, so these are kind of related to this one in the upper left. Okay, we got to first consider whether there are non-bonding or that we have to take into account. Okay, so there's actually 2 pairs on the oxygen, right? So when oxygen is neutral, it has 2 single bonds or a double bond and 2 non-bonding pairs. So now we have to decide whether one or both or none of these pairs of electrons can go into the pi system. All right, so if a molecule can become aromatic, it will. All right, so for this molecule, this is called furan. If furan can put one of those pairs in the pi system, then it's going to have 3 pairs. It could be aromatic. All right, so let's look at how this can work. Okay, so each of these carbons has a p orbital. Okay. Now this oxygen, what would we expect its hybridization to be? All right, it has 4 pairs of electrons around it. All right, so usually that situation would be sp3. And so if that's true, when we have an sp3 hybridized center, then it's not aromatic. Okay, but in this case, we get an unusual thing to take place. Okay, so it rehybridizes to sp2 2, all right, it puts 2 of the electrons in the sp2 hybridized orbital, and it puts 2 electrons in the pi bond, in the p orbital. All right, so in that way, we now have 2, 3, 4, 5, 6 pi electrons. All right, so furan is aromatic. Okay, so this idea of rehybridizing the oxygen. So it costs a little bit of energy to rehybridize from sp3 to sp2 because that's pushing some of the bonding electrons closer to one another. Okay, because, well, it's pushing these bonds, these electrons, because these are now only 90 degrees apart, whereas if it was sp3, they'd be 109.5 degrees apart. So essentially, the molecule has to spend some energy to rehybridize to sp2 to push these electrons closer together, but the payoff is that it becomes aromatic, and so it gets a lot of resonance energy back, and that makes the molecule more stable. All right, so the next molecule is called pyrrole. So, and nitrogen has a pair of electrons. Okay, so pyrrole has a structure very similar to furan. All right, so for pyrrole, it's going to be like this. So now this sp2 hybridized orbital makes a nitrogen-hydrogen bond. Each of these carbon atoms has a p orbital with 1 electron. And the nitrogen can put its non-bonding pair into the p orbital. So this has 6 pi electrons. Yes, this is aromatic. All right, so furan and pyrrole have the same, essentially the same electronic structure. Okay, so we can call them isoelectronic. Okay, so they have the same electronic structure. They both have these 2 pi bonds, and then they have a non-bonding pair that's donated into the pi system. All right, so our last example here is a compound called imidazole. Okay, it's a ring that's also part of an amino acid that we find in biology. All right, so now we have 2 different types of nitrogen. Okay, each of these nitrogens have 3 bonds to them, so each one will have a non-bonding pair. So we have to decide which of those would be in the p orbital and which might be in an sp2 hybridized orbital. All right, so we can kind of use the analysis we've done above. So notice that in this case, the nitrogen already had a double bond going to it. All right, so in this case, the non-bonding pair went into an sp2 hybridized orbital. Down here, the nitrogen had a hydrogen on it, and the non-bonding pair doesn't show any double bonds to it yet, so this pair went into the p orbital. So we can do the same analysis here, right? So this pair here is more like pyridine on the top, so that pair is going to go into the sp2 hybridized orbital. This pair down here is more like pyrrole, so that's going to go into the p orbital. All right, so then when we count up our pairs of pi electrons, right, we're going to have this pair, so 1, 2, 3 pairs. 3 pairs pi electrons gives us 6 pi electrons. Yes, imidazole is aromatic. All right, so we just have 2 more compounds here we'll take a look at. But in this case, what we're going to do is we're going to actually draw out some resonance. Okay? So let's look at this pyrrole at the top. So remember, pyrrole has a pair of non-bonding electrons. So if we want to consider this back, what we learned in the last slide, or the last video, one of the kind of generic systems that we have here for resonance, we have non-bonding electrons next to a pi bond. All right, so we know how to do resonance in this situation. We can take this non-bonding pair, donate it to form a new pi bond, and then those electrons will be pushed over onto the adjacent carbon. All right, so we can draw a resonance contributor for that. Now has a double bond here and a pair of electrons up here. All right, so the nitrogen now has 4 bonds attached. So that gives it a plus charge. The carbon has a minus charge. So in one sense, what we've done here is we've caused a separation of charge, which makes this resonance contributor a little less stable than the first one, but because we can continue this and it generates a lot of resonance, these do greatly influence the character of this molecule. Alright, so we push it a little farther, plus here, we have a new pi bond here, and now the electrons are over here with a minus. We can do it again. We form a double bond here, so that nitrogen can't hold anymore, so it has to go over to here. Alright, so now, let's see, where do we have our double bonds? We have one here, pi electrons here, and non-bonding electrons there, and there we get that. We can do it again. And we have there, here, here's our electrons, the plus right there. We can do this again. And look now, finally, the electrons go back onto the nitrogen. Okay, so in fact, when we go to there, this one goes back to here. Alright, so if we think about what the true structure, or the hybrid structure, would look like for this molecule. Okay, we have this. Here's our carbon, or ring framework. Right? Essentially, we notice that most of the resonance structures, except for this first one, have a plus on the nitrogen. Right? That's going to be a delta plus on the nitrogen. We have partial double bonds all the way around. And where do the delta minuses go? Okay, we've got a delta minus here, 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 and here. Look, it's spread over every one of those carbons. Delta minus, delta minus, delta minus, delta minus. Okay, so this is the hybrid, the true structure. Alright, so the bottom structure here, this is the cyclopentadienyl anion. This is isoelectronic to pyrrole. Right? So we can take this pair of electrons and do the same thing as we did for pyrrole. The only difference is now we start as an anion, and so we aren't separating charge, we just have this anion moving around the ring, delocalizing around the ring. Okay, I'm not going to draw all of these, but maybe you get the picture. If we keep going, essentially we're going to spread that minus charge over every carbon in this ring system. And so the hybrid structure for this one would be delta minus, delta minus, delta minus, delta minus, delta minus. All right. So, in this, we have learned about aromatic compounds and anti-aromatic compounds. We know that aromatic compounds receive a lot of stability of resonance energy by becoming aromatic. We learned about the criteria that the molecules have to have a ring, they have to have a p orbital on every atom of the ring, and they have to be planar. In addition, they have to have the correct number of pi electrons. Right? So they have to have an odd number of electron pairs. If molecules satisfy all of those requirements, but they have an even number of electron pairs, then they're unstable and they're anti-aromatic. All right, so in the next video, what we're going to start to do is look at some of the outcomes or some of the impact of molecules being aromatic.